mafic minerals, or mafic rocks, are about 50% by weight silica. Quartz is made up of iron oxides, manganese oxides, magnesium oxide. I think that's about it. So, and that's what makes them dark. Felsic lavas are usually lighter color, and they are made up of 65% quartz and feldspar, and the rest of it a mix of all kinds of stuff. So I'm going to pass a couple of them around. This is, this is your working glass rock. This is rhyolite. Rhyolite is common here in Utah. This one's really dark, mostly just from dirt. If I took it to a pressure washer, it would be much lighter color, and you can see where it's gotten chipped and stuff over the years, where it's much grayer inside than it is on the outside. But I kind of like it the way it is. So I don't want to break it.
You know, we use that for something, right?
Yeah, a necklace. I love the ones with holes in it. And what causes these holes? Everybody thinks this is a weathering pattern, and it's not. So it's gas. So this rhyolite is flowing across the ground. Think of like a soda froth. You pour it into a cup too fast, it flows everywhere, bubbles everywhere. That froth that you get, that is what rhyolite looks like when it comes out of the ground. It's not an explosive volcano that shoots way up in the air. It just kind of, the rhyolite here in Utah anyway. There are rhyolites that do explode and go way up in the air. But the stuff in Utah was more like a crack in the ground, and it just bubbled up and fizzed everywhere. And so this is gas bubbles that were trying to reach the surface. And some of them did, some of them didn't. And so when you get out to Topaz Mountain or any of that area out to the Thomas Range, you'll see that you've got these big flows that are just made up of all these gas bubbles on top. And that is where the lava was flowing, and the gas bubbles were trying to percolate out of it. So we'll pass that one around. Oh, go down and bring in the salt. I'm going to use this one twice. Okay, so this is what basalt looks like. The basalt is black, it's mafic, it's dark, it's always dark. Think of Hawaii. That kind of lava, it tends to not have a lot of gas in it, and so it flows rather than explodes. And now there's intermediates, and when I say there's this and that, felsic and mafic, there's a graduation in between, and you get all kinds of in betweens. And the more it becomes one, the less it becomes the other. So these are generalizations. There's an intermediate and between basalt and rhyolite or felsic, and I didn't even write notes down now because nobody cares. Intrusive and extrusive is important. Extrusive is when the rock, the magma explodes onto the surface, or flows onto the surface, and you get basalt flows or rhyolite flows. Intrusive is when it cools inside the Earth's crust, and that's when you get granite, andesite, diorite. Those all cool inside the Earth's crust, and because they cool slower than on the surface, then you can get things like pegmatites that have minerals, crystals that grow inside of them. Very rarely do you get big crystals that grow in lavas, whether it's felsic or mafic. And I say that, but then we have Topaz Mountain, where you have the topaz crystals growing in rhyolite. But they didn't form from the rhyolite, they formed from gases after the rhyolite had flowed, and gases coming up to the ground deposited those crystals in there afterwards. So it's a little confusing, a little tricky. The more viscous a lava is, the more violent the explosion will be. So that's the important thing there. Also, temperature and the amount of silica that's in the lava will determine how explosive it is. So if you have really super high temperatures, they tend to be more explosive, obviously. Water boils more rapidly when it gets hotter than when it's cooler. And then the amount of silica, which is causing the viscosity. Mafic minerals tend to cool at about 700 degrees Celsius, which is, we can convert that in our head, 1,300 degrees.
We're American.
Right, yeah. About 1,300 degrees Fahrenheit. Felsic minerals don't cool until about 1,500 degrees Celsius, so almost 3,000 degrees. So that's when they start to cool and solidify. All right, so there's a number of different types of volcanoes, and we're going to just cover a few. Normally I should have big picture graphs. If I was a real professor, I'd have overheads or something, I don't know. You can have your volcano is when the magma pushes up and eventually pops out the top, steam, gas, lava flowing. So the shape of the volcano can tell you what kind of volcano it is. So you can have ones that are kind of low domed and the lava flows in all directions around it. That is what Hawaii is, basically a mountain, a range of slow domed building volcanoes. You can have volcanoes that, so let me back a little bit. You can have the neck is inside here, that's where the lava is coming up. You have the caldera at the top, or the vent. When it's still coming out, it's called the vent. The caldera is when that vent is, everything is escaped. There's nothing left inside, and all the rock collapses back down inside. So that's when you get a caldera, and you can have that collapse, and then another volcano come up inside of it and pop out. So if you've ever been up to in Oregon, Wizard Island, or Crater Lake, yeah, so you can see the little volcano down there in the bottom. I don't know if it's still steaming. It used to steam. You can see the steam coming out the top of it, but I don't know. That may have quit years ago. So, but anyway, so you get that. You can get that caldera collapse and a little volcano popped up through there because it's encased. It gets all the new snow melt and everything in there, so it turns into a lake. There's nowhere for the water to go. It's all just a big ball. A shield volcano. Well, we did shield. So that's Hawaii. What's fun about Hawaii volcanoes is they produce two different types of lava. One is called A-H-A-H. It's just spelled A-A. And you can always remember that one because if you walk across it barefoot, it's really jagged and you're going to be going, the other one's Pahoho, and that looks very smooth and flowing. And that's what you usually see in the pictures of Hawaii lava. Very smooth and flowing lava fields. Very beautiful, very pretty. And I'm sure both of those words come from the Hawaiian language and what do they speak? They're Polynesian. So, pyroclastic flows is when you have a cinder cone, which we have a bunch of cinder cones here in Utah, and they are very steep points. They often point just straight up, and they're very steep angled. They reach the angle of repose, which is the steepest the pyroclastic stuff on the sides can hold without flowing down. So they're often very steep. You can see them down by Richfield, there's a bunch. They're characteristic. So those produce, because it often just bubbles out, or like popcorn coming out the top of it, and it just rolls down the side. And so that's where you get things called tephra bombs. And that's what this is. This is a tephra bomb. So this came flying out of a volcano and landed somewhere. The best thing I can think of that describes these is if you've seen when Frodo throws the ring in the volcano, and then he runs out and there's lava just flowing everywhere and pieces spitting out everywhere. That's this. These are tephra bombs. Also, these are a little small. They're very round, very cool looking. These are from here in Utah. In fact, that one's from Utah too. When they say pumice is the only rock that floats, it's not true. A lot of tephra floats, and it's not pumice. But these ones, because pumice is defined as being a white porous rock, and these are black on the inside with a red coating on the outside.
Where do you find them in Utah?
These are down in Escalante.
Okay.
Is that
That's from Escalante.
Down
Yeah. All right. Another type of volcano is called a composite volcano or stratovolcano. And these tend to be much older than other volcanoes and much larger. They're shallow flanks, but they're made up of basalt flows and tephra flows, and then basalt flows and tephra flows. And some of them can go 100,000 years between each eruption. So they tend to be very old and very layered and very, very thick. And if that last layer is the basalt, then they're very durable. Basalt does not weather very fast. The largest one is, it's in the Andes, and it's almost 7,000 meters high. So it's pretty darn tall. Mount Rainier and Mount St. Helens are both stratovolcanoes as well. Some of the larger ones are also in Canada. They're just absolutely huge. Okay, so volcanic domes are an interesting structure of volcanoes. So you have your volcano, and sometimes after it erupts, it gets a cap on the top of the dome of rock that kind of seals it off. And it can be just inside the vent, or it can cover the whole entire top of the mountain. And if it cools really rapidly, super rapidly, then you get obsidian. If it cools more slow, then you get andesite type rocks that cap it off. And it's neat because we find those here in Utah a lot, where you can go find the top of the mountain and it's coated in obsidian. And then you think, oh, where did this come from? And then you realize, oh wait, I'm standing on a volcano. So, all right, plateau flows. These are large basalt flows. You see these in Idaho a lot. Hawaii is also a lot, where the lava just kind of oozes out of the ground like toothpaste and just flows for a long ways. There are places in Brazil, Asia, where the basalt is literally 3,000 feet thick. Yeah, so you get these dense flows. I mean, you think about 3,000 feet of basalt, that all came out of the ground. I mean, I hate to say it, but it's like you get this zit that pops, and you get 3,000 feet of all right, and so when you get these large plateaus like that, you get the basalt columns. And they're really neat from on top. They look like honeycomb. But if you look at them inside, there are these columns. They look like crystals. They're not really crystals. It's called columnar jointing. Columnar basalts are fun. We have lots of them here in Utah. There's places down by, if you've ever been to Babylon, down in southern Utah, there's a ridge where you can see 2 layers of basalt columns. So one flow and then another flow, and they crystallize, solidified at different times, causing 2 layers on top of each other.
Paul Bunyan's woodpile.
Paul Bunyan's woodpile is another columnar basalt. All right. So the Thomas Range is a rhyolite flow. We talked about that. All right.
Devil's Tower.
The Devil's Tower, is that
Devil's
basalt?
Tower is basalt. Yes, that's. And there's several different theories about what Devil's Tower is. You know, it's the neck of a volcano that solidified. Now they're saying that's not how it solidified. It's just part of a flow. I don't see how it's part of a flow because it literally comes up like that. So I don't know. There are dozens and dozens and dozens of terms for the textures of volcanic rock, both intrusive and extrusive. I'm not going to put you to sleep with those. Seriously, I mean, they are so boring. And honestly, I don't even care.
Like names of our next pets.
Right. I can send you a list. And it's funny because when I was in school, I had to learn all these names, and there's probably, I don't know, a couple of hundred, and we had to not only memorize the words, but we had to memorize what they looked like, and they'd give us a piece. What is this? And I'm like, it's another type of granite. Who cares? So anyway, they're all based on geochemistry and structure, and so you get things like grain size. You know, you can have a granite that's small grain, it's got a name. Medium grain, it's got a name. Large grain, it's got a name. So anyway, I'm not going to go through all this. So volcanoes are seen on a number of other planets, including the moon. The moon has several volcanoes that are inactive that we see on there. Other planets we have seen have active volcanoes on them. So what was the first shuttle that landed on the moon? Apollo 13? Yeah. 11? Whatever the first one was, one of the first things they did was put seismic sensors on the moon, because geologists had theorized that the moon had a core, and like the Earth, even though it was so much smaller, but it had a core, and that hence it would have volcanic activity and earthquake activity. And sure enough, immediately they started picking up earthquake activity immediately, and so it helped develop these theories about the moon, the internal structure of the moon, and anyway, it was an important discovery, scientifically. All right, some terms we are going to discuss. Everybody, like, bring their paper and pen. Yeah. Okay. A sill, S-I-L-L, is when you have it's a concordant structure where you have magma come in between layers of rock. So you have layers of sandstone, shell, limestone, whatever, and magma comes up and goes between the layers. That's called a sill. It's usually more resistant, and so often you see sills sticking up out of the ground like a big fin. A dike is discordant, means it cuts across the layers of rock. So you can have all the layers of rock, and a dike will just shoot straight up through all of them. It just fractures the earth and comes right up through them.
That's lava.
Yeah. Yeah. Some type of lava. Yeah.
Kind of like an extrusion.
Yeah. Yeah. So a lot of people think that the double slide is a dike, but it's not. It's really horizontal layers of sandstone that got lifted up into the position they're in now, and they have more silica in them, and so they didn't erode as fast as the stuff around. Pluton is rocks that form at depth, so any depth. It can be really deep, or it can be pretty shallow, but it's a ball. It's usually a ball shape or an inverted teardrop of magma. A stalk is when that Pluton is exposed to the surface, and so we often talk about the alta stalk. Alta is exposed in Alta in Park City. And a stalk is an exposure of a Pluton that's less than 100 square kilometers. A batholith is when it's more than 100 square kilometers. And you think, wow, we have them that are that big. We do. We have some that are tens of thousands of square kilometers. The Canadian Shield is probably hundreds of thousands of square kilometers. It's massive. All right, a pegmatite is a rock that, this term, I hate this because this term is used not right a lot of the times. So a pegmatite is an igneous rock made up of very coarse grained crystals. So this is a big one here. You can see the pegmatites here. You've got the alkali feldspars, the potassium feldspars, and the mica in here. You can see these are all nice, great big crystals. It's easy to break up. They were all really small crystals. They would be held together really tightly.
The alkali is with the
What's that?
white, right? The alkali.
The white is the alkali, and the pink is the potassic feldspar, and then the mica. And there's quartz in there too. All right, so this is a pegmatite. So when people say go look for pegmatites and find crystals, that's not what they're talking about. Ish. So they're talking about that, but you have to have an open void for the crystals to grow in. And that's what this is. So this is a pegmatite. That one's from here in Utah. This one is from San Diego. And so this one has got tourmalines and morganite and obviously the quartz crystals and feldspar. So it's got a lot. I'm not going to pass that one. It weighs about 8 pounds. Yeah.
So a pegmatite is not, I mean, you don't say, we're gonna go out and look for pegmatite, like a certain rock.
No, well, you kind of are. You're looking for that, but you want something that has voids in it. And that's the problem we have in Utah, is that our pegmatites are lacking the empty spaces in there.
Okay.
And so you can say, I'm going to go look for a pegmatite, and incidentally, a pegmatite can be a round ball inside the middle of a granite, or it can be a seam where you have a dike that cut through other granite, and it's more pegmatitic, and so it has bigger crystals, but it still doesn't have a void in it that anything can grow in. So it can be very confusing.
So it would be like more of a description?
It is. It's both a noun and an adjective.
The mineral mountains.
The mineral mountains are granite. There are these huge granite spires that stick up out of the ground, and in them have pegmatites. So think of this granite formed deep inside the earth, and as it was cooling, gas bubbles were in there. Maybe not even gas, maybe liquid bubbles were in there, and so they allowed bigger crystals to form in there. Now, finding ones that have voids, bugs big enough for crystals to grow in is hard, but it's rewarding because if you go down there and you dig and you find one, you break it open, you can find quartz crystals down there up to 2 feet across, 2 feet long. So, I mean, who doesn't want one of those?
Yeah.
So when you find this, is it like that, or did you have to crack it open, or?
I had to put it in the truck. That's all I had to do.
Okay, just like that.
Yeah, so when they were mining, and so what they do is they're mining through this granite, and they're looking for, and where these come from is very famous for its tourmalines. The green and pink tourmalines have been mined there for hundreds of years. And so they're looking for this granite that has these voids in it. And so they'll find them, and some of them are big enough to walk into, and some of them are, only this big. But they're looking for the tourmaline out of there because they get some bright green and bright pink tourmalines that come from there. And this is San Diego, Palo.
I thought maybe because there's a place in Maine where they.
Maine has them too. Yeah, Maine. The difference between Maine and California, I bet Maine has way more than we know about, but it's covered in forest and greenery because they get so much rain. You go to San Diego, there's nothing growing.
Yeah.
So, yeah, it's easy to find these pegmatites, but that case it's not. So, all right, are we all confused about pegmatites now? Good? All right. Plate tectonics, all of the plates are driven by the convection in the earth, which is all driven by the magma in the ground. The heat's driving the magma around. So everything that we see in plate tectonics is all done by igneous rock. So when you have ocean spreading in the Atlantic where the crack is spewing, they say buy ground because they're not making any more of it. It's not true. Earth is making more ground all the time. There's always, every time a volcano erupts, there's new ground. I'm like, why? It's there. Anyways, as the plates are spreading, the new magma is boiling up out of the ground, out of that fissure, out of that crack. It's going right into the mantle, the upper mantle. It goes right through what's called the metamorphic discontinuity, and that's a layer between the mantle and the Earth's crust. And it's kind of, it's not really a solid, but it's not really a melt. So it's kind of like plastic deformation right there. It's kind of like a little shell, so, which is good because otherwise everything would fall apart. That covers the majority of the igneous rocks we're going to cover. Any questions about igneous rocks? I did not bring samples of pegmatites with tourmalines in them for everything. All right. We're going to cover metamorphic rocks next, and then next month we'll do sedimentary rocks. Sedimentary rocks are important in Utah because so much of Utah is sedimentary rock. So. All right, so metamorphic rocks are rocks that have changed. They changed from changed form. It's Latin. I didn't write down what the word is, but meta means change, and morphic means form. So change form. Most of the change happens at depth. So it's not something that's coming to the surface and changing, although that does happen. Most of it happens at depth. And factors of metamorphism are the composition of the parent rock, what it starts out as, and temperature and pressure. So those three things determine what you wind up with in the end. So, all right. So anyway, the further down you go, the hotter it gets, the more metamorphism you get. Quartz starts to metamorphose at about 800 degrees Celsius. And the other factor is time. It takes time for things to change. So foliated rocks are, when you look at a gneiss or a schist, you can see it's made up of layers or bands. Those are called foliation. Schist usually is foliated enough that when you hit to break it, it'll break apart on those layers. Gneiss does not do that. Now, schist, you have to make sure you say that right. Schist. Schist has schistosity. I did not
Is
make
that
that
an
up.
actual word?
It is a word.
Look it up.
No, I'm trying to find that one rock that we found.
So it's schist, and schistosity is OC whatever TY. Gneiss, when you break gneiss, it tends to break against the foliation because it's not as separated. It's spelled Geneis. Yes. It's pronounced nice. I didn't make it up. So what happens when you have metamorphic rocks is you can have, you can have a stalk or a pluton coming up out of the ground towards the surface of the ground. You get these inverted teardrops. It's coming up. It's pushing things out of its way. You get a little dome, maybe, and it's baking the rock around it. These are hot. They're hundreds and hundreds and hundreds, 800 degrees Celsius-ish. So they're baking the rock around them. And if you look at an aerial view of where these are exposed, and you get this pluton that comes up, and you slice across the top of it, you can see now it's called a stalk, and you can see the metamorphic rocks go out. And the further you go out, you get different rocks. And so the closer to it, you get what's called contact metamorphism, and that's where you get things like skarns that are highly metamorphosed, where it's hard to even tell what the original rock was. We only know because of geochemistry. And then the further you go out, then the parent rock is not metamorphosed at all. So if you have this granitic composition pluton coming up, and you have limestone around it, you're going to have skarns around it where you get well-developed garnets, and then you go out a little bit further and you get things like marbles and various things as you go out. And if you look at an aerial view of one of these, you can actually just see the rings. I mean, they're so perfect. It's really cool. So ore bodies come in usually not in the form of a magma. It can be in a magma, but usually you get a magma that comes up and it fractures the ground, and so now all this groundwater can flow down those fractures, and that's where we get a lot of ore bodies. Mammoth and Centennial are both that way. In fact, almost every ore body in Utah is that way. We have this ring of ore that goes around the Salt Lake Valley. You have Kennecott, Eureka, and on the other side you've got Park City and Alta and all the mines up there. And there's some to the north. And if you look at an aerial view of the ore bodies, there's this big ring right around the Salt Lake Valley. Now, it's a little deceiving because all the mineralogy for all of those is very, very similar. Not exact, but very similar. And we do not have a magma chamber in the middle of the valley. So they formed differently, and it's a study. It's an area of great study, and I don't have the answer to that. All right. Going back to the rock cycle, we have granite up in the mountains. Granite weathers to become what out on the beach?
Sand.
Sand. Sand gets buried out on the beach to turn into
Sandstone.
sandstone. And if it gets buried deep enough, what's it turn into? Quartzite. Quartzite. So anyway, that takes a little bit of heat and a lot of pressure. In fact, it has to be about 3,000 feet thick for the quartzite to form. So. Regional metamorphism also requires a confined space. So it cannot have any place to go to. It has to be confined to its system. So we have basalt, and it's going to turn into amphibole. Amphibole minerals are things like types of jades, epidote, hornblende, augite. Those are common ones. Oh, and garnets. Shale turns into mica schist, which is a little confusing because if you think about having a shale, it gets metamorphosed and turns into schist. Granite also turns into schist under certain conditions, so it can be very confusing. So if you go up to Farmington, you go up to Farmington Canyon, and you look at the Farmington complex, you get all these granites that have been highly metamorphosed, and you get schists and gneiss. It does not come from shale. But if you go out in the West Desert and you find some of these contact metamorphism places out there, we have the hot magmas that came up, the rhyolites, you get the limestone has turned into schist as well. They're almost impossible to distinguish. When you get schist, you tend to get garnets, starlites, and this is a piece of schist. This one's highly weathered, but you can see there was mica, and there's lots of quartz here. You can see on the sides where it layered into the schist, or the quartzite and the mica. This has got lots of starlight crystals in it, and a big garnet here that's broken off. Gneiss, when it becomes metamorphosed, becomes foliated, meaning it gets layers. And sometimes you'll be looking at a big piece of all the layers, and there'll be this like ribbon of other rock that goes through it. And those are so cool. They're called tigmatic folds. And it's where another rock has been squeezed and it had nowhere to go, so it just kind of does these little zigzags through there. They're very common up in the Farmington complex if you go up there. So, all right, we kind of touched on metastatic alteration. That is a type of metamorphism that does not require much heat or pressure. It is a chemical change, and you have to have the addition of ions. We're not talking about the cars. So you get the ions that come from groundwater, they can come from atmospheric water, they can come from a number of different places, or a number of different types of ions, chemicals that are in the ground as they start to alter, decompose. You can get different minerals that form from that. Let's see, layers within schist and gneiss can be pressed, and then fluids with potassium, sodium, silica, and oxygen come in and alter the schist or gneiss into granite. It's a very special type of granite that does not require any heat. to produce. So it's kind of weird. It's a very weird metasmatic alteration. It's called granitization.
Granitization?
Yeah.
Sounds like
There's only
something
one
else
Z,
made
but
up.
it always comes out with three.
Oh.
Granitization.
Granitization.
Yes. I don't know of any of this in Utah. It is more common in Brazil, Australia. I don't know of any of it around here. So. Hydrothermal alteration, that's when we're talking about what Tony was talking about, the mineralization coming in from hot waters, hot fluids. This is a rock that's been highly altered. It's been turned into, it was limestone that originally, it's been altered into actinolite, it's the big blades of green. If you turn around in the light, you'll see that there's chalcopyrite and molybdenite in there. Look for the bright piece of aluminum looking foil stuff there. This is a schist. You can see that it's foliated schist. It's got the layers there, it comes apart, grains. Well, this one is actually jade, and jade is formed in metamorphic environments. Under certain conditions, you get jade, and that's what this is actually. It's called Bitch Creek jade. It is from Oregon. When the Teton Dam broke, one of the reasons it failed is because they didn't realize that these jade boulders were accumulating in the bottom of the dam, and they were much heavier than what they built the dam to hold. And so when the dam failed, these literally went through the town of Chalice like bullets in the water. They found them lodged in foundations. They found where they've gone through foundations. They found them lodged in huge trees. Literally, this is what was so destructive about that dam failure. When the dam broke and the flood came through the town, they had pieces of pumice the size of houses floating down Main Street. As cool as that would be, it's sad that it happened, but
Yeah.
I wish somebody had photographed it. And you wash the dirt and see what you find. You can keep anything you find. They have a gift shop, and I liked that piece.
Oh, you got that.
Threw that in your backpack and
Yeah,
put it out the door.
I wish. You let me drive up to it. We bought that piece of quartz in there too. This is also from there. This pink quartz. So what you get, the guys were talking about the spirits that were laying on the ground up there that were the size of humans, and they were like, I don't understand. They got up there and there was these quartz crystals, double terminated quartz crystals laying on the ground at 60 feet long, and they were literally covered this ledge where they were at, and hundreds of them. And the locals thought that they were spirits of past people, their ancestors. And so when they pegmatite, you can get big crystals. The biggest quartz crystals in the world do not come from pegmatites, but some of the biggest ones that are around come from pegmatites.
Is it the Wrestler mine that has the molybdenite and the
Yeah,
actinolite?
they
In fact,
form a
I
little
bet that's where this came from.
The big amethyst geode here, Maria, will you uncover amethyst geodes? But until these were discovered, amethyst was ranked as rare and valuable as diamonds. Queen Elizabeth had a beautiful necklace of amethyst, really deep, dark purple amethyst, and it was valued priceless. Now it's considered valueless.
What's this?
Jade, thick. And these amethyst geodes are the gas bubbles in the bottom third. And so they have to mine from the sides because they're not going to mine 2,000 feet of basalt to get to. So yeah, go look at that. You can't tell it's from basalt on the outside because they paint the outsides of these. And they often coat them with cement or plaster to hold them together, which is a museum. It's still there. They couldn't get it in the house, so he had to put it outside, put it in a cement foundation, and built a greenhouse over it.
So when you